Alright guys, let's do this very easy problem where they want you to determine the reactions at the supports. So basically, as you can see in the A, you have only a positive AY reaction, only a reaction going up. It can go to the side. And B is anchored, so you have a positive reaction, BY, and a possible horizontal reaction. However, as you can see, the distributed load is only going down. There's actually no force going towards the left or towards the right to affect this assembly. So there is no horizontal reaction for B. So B in the X is equal to 0. Can tell you that right away. Then if you look at the distributed load, we got to replace it with equivalent forces. And as you can see, we have two shapes. We have this triangle right here, and we have this long rectangle right here. The long rectangle can be replaced by an equivalent force acting right in the middle of the assembly of F1. And the small little triangle can be replaced by an equivalent force, F2, acting one-third from the tall edge of the triangle. So the first thing that we need to do is find F1 and F2. F1, which is the equivalent force acting for the rectangular distributed load, is given by the area of the rectangle. The area of the rectangle is the height, which is 600 newtons per meter, times the width, which is 3 plus 3 is 6 meters, divided by nothing, it's a rectangle, I'm sorry. So it's 600 times 6, and it is equal to 3600 newtons. So that's F1. F2 is the area of the triangle. Remember, you gotta divide by 2 in the end. The area of the triangle is given by the height of the triangle, so from here to here is 300 newtons per meter, because this is 900 and this is 600, so from here to here is 300. So it's 300 times the length of the triangle, which is 3, divided by 2 because it's a triangle, and the area you gotta divide by 2. So it's 450 newtons. So we're replacing basically this distributed load with these two equivalent forces acting on this assembly. I just erase it so you can see it easier. But in the test you have to picture it in your head or draw it really good. So this F2 is acting obviously over here, not up there in the air. So we have F1 and F2 already, and we replace them with these two equivalent forces. So now the problem becomes very easy, as you can see. So let's find AY first. The sum of the moments at B is equal to 0, right? Let me erase this. So let's assume counterclockwise is positive. So the first moment created by F1 is given by the distance times F1. So this is F1 times 3 plus the moment created by F2, which is this distance, which is a distance of 5, of course. So it's F2 times 5 minus this distance, because the AY is turning this whole thing clockwise, so it's minus AY times the whole distance, which is 6, and that is equal to 0. We already find F1 and F2, so you go ahead and you plug them in, 3600 and 450 respectively, and you solve for AY, and you get that AY is equal to 2.175 kilonewtons. And then to solve for BY, you can do simply the sum of the forces on the Y is equal to 0, assuming this orientation, of course, X, Y. So you get F1 going down minus F1, you got F2 going down, you got AY going up, and you got BY going up, and that is equal to 0. You have F1 already, you have F2 already, we found them, 3600 and 450, and we just found AY just a second ago. So you go ahead and replace it, and then the only variable that you have is BY, and you go ahead and you solve for By, and you get that By is equal to 1.875 kilonewtons. Final answer for Ay and final answer for By. And remember, there's no Bx because forces are going, the distributed load's going straight down. There's no horizontal force that will make a reaction at B horizontally. So final answers.